Again, I'm sorry for these hiatuses because I've been a little busy with college. But tonight I have a little bit of time, and you guys know it already. It's Valentine's Day. It's February 14th, and that means a new special episode or a new special lecture that's based on relationship theory. So, last time we talked about category theory and how relationships are a certain kind of object in a category called rel. We talked about the category rel, and a relationship is an object inside this certain category. So let's call a relationship R, and it is an object of rel. I'll use the element symbol. And or rather, yeah. And rel is constructed from the set of all human beings, and the morphisms are the relationships themselves. So that's what we discussed last time in this course. And today I want to go back to graph theory. I want to return to graph theory and our perception of relationships as graphs. So, so today, invariants, graph invariants. So how do we begin with this? So recall, I want you guys to recall the definition of a relationship in terms of graph theory. A relationship between n persons is a directed graph, or maybe an undirected graph, between or on n nodes, where each node represents a human person. Relatively straightforward with representing a relationship, right? Now, today I want to talk about, or I want to introduce you guys to classification of these relationships, or rather, I want to introduce you guys to associating these relationships to certain mathematical objects, wherein I can reconstruct the relationship just from looking at that certain mathematical object, and I can differentiate, varying relationships just by looking at their associated invariants. So one way of talking about those invariants, or one invariant that's possible that we can construct for these objects or these relationships, is homology. A homology group. I know it's a bit of a stretch, but if you somehow have a relationship that loops in on each other, so something that goes like this, that isn't open, rather, even if it's open, you can still construct a homology group of it. You can just interpret this as being sort of isomorphic or homeomorphic to a circle, topologically speaking, and from there I can construct a homology group for that, right? Or if it's just a relationship between two people or a crush, I can of course interpret that as a line, or if it goes both ways, I can interpret it as another circle, and I can construct homologies or homotopy groups from those. But today I want to do something much simpler. I just want to talk to you guys about something called the incidence matrix. Okay, instead of a bird, I have puppies chirping in the background. Okay, so I want to talk about the incidence matrix, and this is like the simplest invariant that you can construct from a given directed graph. So let's say I have a relationship between these four people. I'll call them person A, person B, person C, and person D. And let's say it goes in a clockwise manner like so. And let's say that A likes C as well. So yes, he or she has two crushes. And B likes A back. So it's like a sort of mutual understanding between A and B. So how do I construct the incidence matrix of this graph here. Let's call it, or this relationship, let's call this relationship X. So what is the incidence matrix? I'm going to denote the incidence matrix via M alpha beta of X. And here's how the procedure goes. So first I'm going to list each of these guys as either the row or the columns. I'm going to use the convention wherein we're going to list them as the rows of the matrix. So I'm going to go A, B, C, and D. And here's my bracket. And then I'm going to list them again as the columns. A, B, C, D. And you'll see why I did it in a moment. So what I'm going to do is I'm going to look at the graph. And I'm going to see if... Okay, so we'll consider this over here. We'll consider this as our basis for constructing picking our entries. So the entries of an incidence matrix is only 0 or 1. It's not any other number. Okay, so the rule is that if this node over here, or in this spot, we're considering this node. If this node has a relationship or has a directed edge going from this node to this node, we say it's 1. 0 otherwise. So let's do this for example. Okay, so from the graph we see that A does not have a directed edge going to itself, so it has no relationship to itself. It's not narcissistic, so we'll say 0. Next, let's consider A connected to B. So is there an edge going from A to B? Yes, there is, so we'll put down 1. And then same thing with C. Yeah, there's a 1, but D doesn't really have one, so it's 0. Next for B, now it has an edge going from B to A, so we'll consider it as a 1. Going to itself, no, so 0. Going to C, yes. Going to D, no. Next, C doesn't really wrap back down. C doesn't wrap back to A, so that's a 0. Not for B either, not to itself, but to D it is connected. And D, it's not connected to anything else. There's no directed edge going to any other node apart from A. So I'm just gonna write down 1 for A and then 0 for everything else. So there you have it. That's my incidence matrix. So the incidence matrix of my relationship X is essentially this over here. So 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, and 1, 0, 0, 0. And you guys can tell right away from how I constructed this matrix is that for n amount of nodes or n amount of people in your relationship, the matrix will essentially be an n by n matrix with entries either 0 or 1. Okay, let's do another example. Let's say it's a simple two-sided relationship, but let's say one of the person exhibits some form of narcissism. So let's go from A to B, and then B likes A, and let's say that B likes themselves a little bit too much. So there is a sort of relationship from B to itself. So I'll call this one Y. What is the incidence matrix of my relationship Y? So I'm gonna give you guys a second to do that, judging by from the algorithm I just taught you. So yeah. Okay, let's do it. So from A to itself, we got nothing, so that's 0. From A to B, there is, so that's 1. So I'm writing here A and then B. That's my convention. And then this one here is A and then B. Okay. Now for B to A, there is, so it's 1. B to itself, there is a directed edge going from B to itself. That's another 1. So there you have it. Now the reason why I want to talk about incidence matrices of directed graphs is because not only are we able to extract what exactly a relationship looks like just by observing what these incidence matrices are and establishing the convention on where they were constructed, off of where they were constructed, when we modify these matrices, it reveals some other things, or it modifies the relationship that they represent. So essentially, if I do something like, say, I want to take the transpose of a certain incidence matrix, it's gonna change my original relationship. Okay, what do I mean by that? I'll show you guys. What do I mean by that? So I'm gonna go back to X here and the incidence matrix. Okay, so the incidence matrix of X again is the following 4x4 matrix. It's 0, 1, 1, 0, 1 0 1 0, 0 0 0 1, and 1 0 0 0. So what happens if I take the transpose of this matrix? So m alpha beta t. Of course, I just flip every element along the diagonal. So the diagonal stays the same. These two are the same number, so really they just stay the same. These two over here will have to switch places. So this over here is gonna become a 1, and this third element in the third column, or rather this third element over here is gonna stay a 0. How about this one? So I have these two over here, this is gonna switch, and then these two over here, this is gonna mirror, so this is gonna be a 0, this is gonna be a 1. So these are both zeros, so they're just gonna stay as zeros, and then lastly these are gonna switch. Okay, so that's the transpose of my matrix, or my incidence matrix. So what happens to the relationship as I take the transpose? So I'm gonna list down A and B, and then we're gonna go backwards and reconstruct what happens, or construct what happens to our relationship. So I'm gonna leave those as blank for now, and I'm gonna put down my convention, A, B, C, D, A, B, C, D. Okay, so A to itself, nothing. So A to B, there is something. Next, A to C, there's nothing. A to D, there is something. Okay, next, B to A. Okay, B to A, there is something, so I'm gonna lay that down. B to A. Next, B to B, there's nothing. B to C, nothing. And B to D, nothing. C to A, there is a relationship. C to B, there is something. C to D, there's nothing. And for D, you'll notice that it only has a relationship with C. And wow, that's pretty strange, because okay, it doesn't look obvious right now, but I'm just gonna redraw these arrows over here, these directed edges, as such. Yeah, and then goes like this. And you guys will see that everything has been flipped. So originally, in my original relationship here, A has a relationship to C. So it could be a crush, it could be like A considers C to be his or her hero or idol. Now this time it's the other way around. This time C has a crush on A. And of course, this same thing happens between A and B. The relationship stays the same. It's just that they've been sort of permuted or switched around. Or I certainly like changed the look of it, but it ultimately doesn't change. And that's an identity of this thing. So if I have a relationship containing two people, A and B, and I take the incidence matrix of them, so let's say it's a mutual understanding, or it's a full-fledged relationship where they both like each other, then the incidence matrix, of course, would be a 0 1, and then that will be a 1 0. But I want to switch the convention a little bit so that you guys can see this. I'm gonna put the ones along here. So this is gonna be BA, and then this is AB. So this is BA. I'm gonna establish as BA and then AB. You guys will get a diagonal matrix, an identity matrix. Okay, it's essentially the same thing. It describes the same kind of relationship, except this time we have the identity matrix. A 2x2 identity matrix that represents or is the incidence matrix of this relationship. So if I use the convention BA-AB, notice that this is a 1, this is a 1, and this is a 0, 0. That is essentially the identity matrix for the 2x2 case. A 2x2 identity matrix. And that's pretty cool. Now, for a relationship containing 3 people, that's going to be a bit complicated. I'm going to do that here, just right now, the space. So I got A, B, and C. And then each of these guys goes like this. It's going to be a bit more complicated than that. A, and A likes C. So what is the incidence matrix of this relationship? So the incidence matrix is going to be something like this. So A not to itself, but to B is going to be 1. So although it looks like something that would have an incidence matrix that's the identity matrix, it's something else. So this is something that's sort of like a polyamorous relationship. If you allow that the graphs would represent some sort of transposition, or it would be transitive, you could say. If you claim that these arrows are transitive, wherein because A likes B and B likes C, A likes C, then it's a full-fledged polyamorous relationship expressed in the most simplest form. Okay, so A doesn't really like C, it doesn't seem like it, so that's a 0. Now B likes A, so that's that, and B likes C, so there's that. Yeah, that's a 0. Now C likes A and B, but it doesn't like itself. There. No, A also likes C, so there's that. And although it's not the identity matrix, notice that when I take the transpose of this incidence matrix, it's the same. So I'm not going to write it here anymore. You guys can already see by the diagonal and the entries over here that this is a symmetric matrix. Right? A symmetric matrix. And of course, recall from our position theory that a matrix is symmetric when, if and only if, its transpose is equal to itself. Okay. So I don't really want to drag this lecture on too much. I really just wanted to talk to you guys about the incidence matrix because I thought it's a really, really handy tool for constructing matrices, constructing relationships out of simply these simple algebraic objects, these array of numbers, which you would think were just some random, boring mathematical object, can actually describe a relationship, right? So there's that. That's an incidence matrix. That's one way of associating these relationships to mathematical objects, apart from, of course, going the abstract algebraic approach and using homotopy or homology to classify these things. And of course, it's a more narrow way of talking about them, because homology groups, especially if I created them in the way that I described over here, there would be certain relationships that, although they look the same, actually have, although they look different, have the same homology group. For example, this over here, this looks like it could be just a line, because there's really only two people in it. And if we were to consider this as an undirected edge, because of course when we consider an undirected edge, that means it's a reciprocating relationship, right? That's how we denote these things. Of course, that would simplify my notation here as being A, B, C, and then they're just being connected by a line without an arrow, right? So I could interpret it as such, but of course, topologically speaking, we have two edges, right? One running from here, one running from here. So it could be considered as a circle. Likewise, for this over here, I could consider them as a polyamorous relationship. It goes like this. If, again, we consider the edges to be transitive in like the loosest sense of the word, wherein love is sort of transferred from one person to another. Well, of course, I can interpret this as a circle, or I can interpret it as a bouquet of 4 circles. So this would be either homomorphic to, okay, literally speaking, if we were to interpret this as literal constructions from the one cell, then that would be either homeomorphic to S1, 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 S1. So a bouquet of 4 circles, and or it could just be interpreted as one copy of S1. And as part of the ambiguity that comes from homology, so I want to introduce you guys to a more narrow way of identifying these relationships or telling them apart just by constructing a mathematical object for them, a unique mathematical object for every relationship. Of course, again, relationships are very complicated things. I cannot just boil them down to these sort of lines between circles or these lines between nodes. Relationships are more often than not more complicated than that. But I just wanted to give you guys a sort of small introduction to this kind of classification of relationships, this unique classification. So if I want to go a bit higher, if I want to discuss this in more depth or in a more abstract sense, I'd say that the following definition. So let X be a relationship. Okay, so it's a relationship, it's a directed graph or an undirected graph. The incidence matrix should call M alpha beta of X. Alpha beta are the indices that tells me the coordinates of my elements. Of course, you guys already know that. Of course, this thing would be a member of n tuples of 1, so it's an element of a subgroup of the general linear group on R, so it's going to be a subset. So it's an element of a subset A of the general linear group of n. So I'm going to say this, let X be a relationship of n persons. GLNR. You guys already know the general linear group would entail only square matrices, because non-square matrices, of course here in GLNR we're only considering square matrices, is the matrix with entry. So I'll call the entry A alpha beta, and that is essentially 1 when there exists a relationship between that first element, so I'll call it alpha and beta. So the alpha person to the beta person. So alpha row to the beta, alpha column to the beta row, or in this case alpha column to the beta row, and 0 likewise or otherwise. So that's my definition of the incidence matrix of a relationship in a more abstract sense. Okay, so of course every matrix that contains zeros and ones as its entries would be part of this general linear group. And the determinant of these matrices are our way of further compactifying this thing, because if I want to talk about these kind of relationships and I want to differentiate between these two, I can talk about the determinant of their incidence matrix. And especially when they are different people and have different dynamics between each other, their determinants or the determinants of their incidence matrix would be different. So for example, let's take the determinant of this graph over here and this graph over here, or rather this relationship over here and this relationship over here. The determinant of this relationship, or the incidence matrix of this relationship, would be 0 minus 1, so that's negative 1. Okay, and the determinant of this one would be 1 minus 0, so that's 1. And so I can say definitively that these are not equal, because the determinant of this incidence matrix is negative 1 and the determinant of this incidence matrix is 1. So I can say with absolute certainty that if I were to reconstruct their relationship that is represented by this incidence matrix, it would be different from the relationship I would have reconstructed from this incidence matrix. Okay, so that's really it when it comes to incidence matrices. It's a really fun tool if you guys want to just like play around with relationships, like say you know a group of friends that share this kind of dynamic, like say you know a couple, you can tell them, hey, if I were to interpret your relationship as a graph in graph theory in mathematics, I know it's a bit nerdy, but I can construct this thing called an incidence matrix, and you guys can do what you will with that information or whatever. You guys can be like a total nerd about it or something. So that's really it about the incidence matrix. There are other matrix invariants for graphs out there. There's, of course, the adjacency matrix and the Laplacian matrix. And there it is again. The Laplacian, okay, I had to cut that. So adjacency matrix and Laplacian matrix, two other sort of things, two other matrix invariants that I will discuss in a different video. So this is very short. I know it's very short, but yeah, I think I'm just gonna splice this into the actual video on my editor, and I'll submit that. So that's really it for this lecture. Again, I wish you guys a really happy Valentine's Day. I know my Valentine's Day isn't really that great this year. It wasn't that great last year either, but you know, that's why we live, so that we can try things again and again. So, you know, have a great Valentine's Day. I hope you're not too heartbroken because of someone that you thought that, you know, she or he was the one or they were the one. But I hope you guys at least got some joy out of this, or got some nerdy stuff out of this lecture for Valentine's Day. So that's really it for this lecture, and I will see you guys in the next one.